right, next up on our weekly video series, we have week 5 theory. Some of this kind of piggybacks on week 4. So when we talked about op amps, we're going to do a bit more on that topic, and then a couple other things at the end. So a lot of this is kind of similar or be a review of what we saw in last week's video as well. So we saw the rules for op amps, how to power them, and some variations. Today we're going to begin kind of review those things and then see a couple more variations and then move on to some other applications and limitations of these operational amplifiers. So the rules, good to go over those again. So rule 1, any ideal op amp open loop voltage gain is infinite, practical purposes, 10,000 to a million. Input impedance is very large, output impedance is very small. That basically leads to lead 3 where the input terminals of an op amp have basically no current, so you can assume, we will assume we have the ideal op amps where there's 0 current going into either plus or minus input. And then anytime you have negative feedback, an op amp's trying to respond by driving those two voltages to be the same, so V plus and V minus. With the difference, V plus minus V minus equals 0, or V plus equals V minus. Same deal there. Ways to power them. So again, these op amps need power. There's power inputs for them that you need to hook up when you do your circuits in lab that you may have seen last week. And so a couple ways to get that positive negative voltage that you may have done. Then the variations that, again, we've seen last week, there's the unity gain amplifier or buffer, which has a gain of 1, and then deriving that gain equation. The inverting amplifier, so this, with this negative feedback to the negative input, is going to invert the input signal, so minus sign there, and then the amount it invert, or the amount of amplification is given by the ratio of the two resistors. So R2 over R1, in this case, would be negative 10. So the V out would be 10 times the input voltage, but again, inverted. So minus sign or 180 degrees out of phase, depending on whether it's DC or AC. Non-inverting amplifier, so actually not being inverted. There's a circuit for that. Again, gain in this equation. Gain for this op amp is given by this equation. You can derive last class. And then summing amplifier, so we have more than one input. This one only has 2. You can have a lot of them, as you may have seen in homework. So this just adds all the gains. This happens to be a negative summing amplifier to the negative terminal. So these get inverted, minus sign, and then R3 over R1, similar to having multiple inverting circuits essentially. Add it all up is your V out. So a couple new variations that we didn't see last week. The first one is the integrator circuit. So instead of having a resistor both after V in and from the negative feedback loop, if we replace that resistor in the negative feedback loop with a capacitor, the output ends up being the negative derivative of the input. So again, going into the negative input terminal, so it's negative, and then the capacitor actually turns it into the derivative in time. So my output voltage in this case is the integral of 1 over RC times the input voltage integrated with respect to time, as we've seen. So if you had a square wave coming in, you'll get a triangular wave going out. So derivative, I have some positive slope, some negative slope. So that's why we have that as V out. Way to derive this V out formula, you have feedback. So rule 4 is going to tell you that my two voltages, plus and minus inputs, are the same. I know that V plus goes to the ground, so V plus and V minus go to 0 in this case. No current enters either input, so in terms of the top one, the current in this little branch here is 0. So that means the current IR has to be the same as the current IC, both coming in, technically negative the way they're drawn. So then from Ohm's law, the current through my resistor is the voltage drop, in this case V in minus V minus, divided by that resistor R. V minus is 0, so that's just V in over R. For my capacitor, same deal. I can take voltage loop around here. So V out minus V minus again, but V minus again to 0. And then for my current in my capacitor, it's C times D voltage over dt. So voltage in the capacitor, V out minus V minus, which is 0. So C dV out dt. So I solve that for dV out. Negative dV out is 1 over RC, negative 1 over RC times V in times dt. And then obviously that integral gives you that integral. An application of an integrator op-amp circuit is that you can find the average or mean value of any function over some time. So any general function, you can find the mean by taking the integral of it. And so this op-amp can be used to calculate the average voltage, because that's what the op-amps, or that's what we're measuring in this case, is voltages, V out. So I can find the average of that V out by using these integrator op-amps. If you have a integrator, might as well have a differentiator as well. So something to integrate, also have something to differentiate. This is similar to the circuit we had before, but alternate the positions of the capacitor and the resistor. So kind of like how we did this for the high pass and low pass filters, just alternate which one you take. Same deal here, just kind of reverse them, and that does kind of the opposite. So in this case, I have a differentiator. Again, I have a negative derivative in this case because I'm into the negative terminal. So negative derivative in time, so my out is the derivative of what's coming in. So again, here coming in, I have some positive slope, some negative slope. So positive number, negative number, positive number, negative number. So positive, negative, positive, negative. That's my out signal. Derive that very similar ways. I have 0 for the ground, that's V plus. V minus and V plus are the same because of negative feedback. No current goes in, so these two currents are the same, technically with a minus sign. And then very similarly, current over the resistor, Kirchhoff's law, current to the capacitor, again Kirchhoff's law with the voltage in the capacitor, V minus is 0 the whole time, so V out is just RC dV in dt, the minus sign. You can also add some compensation, capacitors and resistors. We saw that in the previous slide as well. That just helps smooth out some of the results. So these integrator and differentiator circuits are very useful in what's called PID control. So an example of where you would use that is if you want to control the position of an aileron by using an input. So you input some voltage to it to change its position. So how are we going to do this with what we just learned? So one option is to change the voltage proportionally to the deviation from the desired deflection in the actual position. And so then what do you do when the motor actually reaches that location, because you want it to stop there to keep that aileron in that position. And so the way this is done a lot is with what's called PID control. So PID basically stands for proportional, integral, and derivative. So you're using one of those three methods, or one of those three types of op-amps to give the signal that you want to make the motor do what you want. And so you're basically looking at what is the difference between where you want the aileron to be and where it is right now. And based on that difference, you can make a PID controller that takes that difference as the input, and then you have your op-amps and the circuits to control and make that go where you want it to go. Another variation of an op-amp circuit is called a sample and hold circuit. So you include a switch into this, a capacitor and a resistor with a unity gain op-amp. So the op-amp acts as a unity gain amp or buffer. What's going to do is going to send the capacitor voltage to be out anytime this switch is open. When the switch is closed, it's basically charging up your capacitor, and then when you want that voltage to be output, whatever the capacitor has been charged to, that's when you open it, and that's when you get that signal out. The next variation is a peak detector. So it's very similar to the previous circuit, other than include a diode as well. So what this is basically a variation of the sample and hold circuit we saw previously, but this kind of holds that maximum value intact. And so it holds that until a bigger value is obtained, and it holds that. So eventually by the very end, you end up with the maximum value or the peak. That's why it's called the peak detector. So again, we have an op-amp that acts as a buffer, just like we did before. But what the diode does is prevents the capacitor from discharging when the input drops below the peak. And so your output, so this kind of wavy thing is what Vin's doing, and then V out, your whatever is the biggest number, that's what's kept. So down here, this is the biggest number, then this is the biggest number, Vin goes down, but V out keeps the biggest number, then it gets a little bigger, so it keeps that one, gets a little bigger, so it keeps that one, and so on. So again, you see it's always going to keep the biggest voltage, and a more realistic peak detector circuit shown there. As we saw last class, you can combine a lot of these. So there's a combination, same one we saw last class, have an inverting amp in series or connected to a summing amplifier. And so again, that just happens in stages. So my summing amplifier, I'm going to get some V out here, and then this is going to invert it and amplify it as well. And so you have different stages, different applications, as we saw again. So we saw last class in open loop operation, the op-amps hit the rails fairly quickly. So if you input the input voltage, it amplifies it, and very quickly that hits the VS source voltage, the maximum voltage that can be produced. And so your output jumps very quickly between plus VS and minus VS. You also probably saw that in some labs. So what this leads to is something called a comparator circuit. So a comparator circuit compares the input voltage to some reference voltage. So in this case, you're comparing it to ground essentially. And so if I put a V in into my circuit, if that V in is larger than my reference voltage, then it's going to output a whatever the maximum voltage is in the positive direction. If that input voltage is less than that reference voltage, is going to output the negative maximum. So that's kind of what's seen in the non-inverting setup. Any voltage bigger than 0 just outputs positive VS. Any input voltage less than 0 outputs negative VS. And so a comparator circuit is very similar to this, but instead of having 0 as a reference, you can have any value as a reference. So I can hook up some other value to the negative terminal in this case instead of ground. And then that's going to be my comparison. So again, if the V in is bigger than that, it'll jump up to positive VS. If the V in is less than that, it'll jump down to negative VS. And again, you can also have it in the inverting setup, where it's just the opposite. So if my input voltage is bigger than whatever this reference is, it'll go to the negative. If my input voltage is lower than that reference voltage, it'll go to the bigger one, because again, it's inverting, so that's the opposite. So we actually have special IC chips called comparators that do the same thing. So comparators and open loop op amps are very similar in their behavior, but there are a couple differences. Comparators are optimized for fast switching between the rail voltages, the maximum voltages. And so this is useful for many applications. The comparators don't use feedback. They're also not optimized to have a linear relationship between the input and the output. So op amps generally have V out is proportional to this voltage difference that we've been seeing and been using. So we found the gain, and the gain is just some number. In this case, it's not a linear relationship with comparators. The symbol for a comparator is the same as an op amp. And instead, it acts a lot like a switch. So either it goes to positive Vs or it goes to negative Vs for some voltage bigger than or less than whatever the reference voltage is. So in this case, V minus is my reference voltage. If V plus is bigger than that, it goes to positive Vs. If V plus is less than V minus, it goes to negative Vs. So far, everything we've talked about in terms of op amps has been using a DC input voltage. So my voltage in has been some constant value. There's no reason why I can't hook this up to an AC source. So that might be in vary. So that's what we're going to look at now. And so to make a few little minor modifications to some of the notation. So the gain before for this simple non-inverting op amp, V out over V in is R1 plus R2 over R1. That's just what we had before. We called that the gain or AV. I want to now specify that and call that AV0. So AV0 specifically refers to the DC voltage gain. So everything we've seen before is the AV0 gain. Now the problem with the AC source is that the transistors and op amps don't react instantaneously. There's a slight delay. The delay is going to depend on the op amp. Most of the ones we use in lab is roughly 0.2 microseconds, so that is relatively fast to the human eye. But if you have a relatively high frequency, that's not necessarily that fast. So we're going to look at now what happens when we increase the frequency of our AC source. So for a sine wave, my delay is manifested in terms of a phase lag. So I have some delta t difference. Again, this is like that 0.2 microseconds that we saw before. So my V out is shifted slightly from V in. And also the amplitude is changed based on the gain. So low frequency is not a big deal. As I said, if this is a low frequency sine wave and delta t is relatively small, there's hardly any variation. If you go to higher frequencies, your output can actually be 180 degrees completely out of phase. So V minus is negative V in, and that's positive feedback, and you don't want that. If you have no signal at the input, the natural internal fluctuations inside the op amp get amplified by this positive feedback, and that's going to generate its own sinusoidal oscillation at some frequency, F OSC. And this oscillation makes the op amp unusable, so that's why you don't want that. So op amps actually have a built-in filter to suppress this oscillation. They have a built-in low-pass filter. So really what we have in our op amp, instead of just being plus and minus inputs, really there are plus and minus inputs in addition to a RC circuit. And so I have some time constant, tau equals RC. That's inside the actual bigger op amp. And so for any time I have a frequency that's larger than the oscillation frequency, that turns the gain down less than 1. And so that suppresses all those oscillations, so it kind of filters them out, just like a low pass filter would. Low pass filter keeps the low frequencies, filters out the high frequencies. So that's what this combination is doing. And I said that's built into all these op amps. So they have their own internal time constant and their own low pass filter built in. So what does that do to the output? Well, because I have this low pass filter, if I'm putting in a relatively high frequency, so one that's close to the cutoff frequency, then I'm going to have some attenuation in my gain. So the gain will actually drop down, and it'll drop down by the same factor that we saw for the RC filters a few weeks ago. So my AC gain is my DC gain, G0, divided by the same factor, the square root of 1 plus omega tau squared, which is the same thing as 1 plus F over F1 squared, where F1 is your frequency, characteristic frequency based on that time constant, 1 over 2 pi tau. And again, G0 is my DC open loop gain. If I have high frequencies, so F much bigger than F1, this is going to attenuate roughly as F1 over F. My gain is going to be factored by the DC gain by the same factor, F1 over F. So it's going to drop down pretty fast, just like we saw with the low pass filters. You can now define something called the unity gain frequency. So FU is the unity gain frequency. So that's the frequency at which I have a gain of 1. So that's, again, in this AC setting. So essentially I have some DC gain, G0, that's some big number, but then I'm using a relatively high frequency, which exactly compensates for that gain. And so my unity gain frequency is essentially exactly that DC gain factored out. So G in this case is my unity gain frequency over the frequency. So if my frequency coming in is a unity gain frequency, my AC gain is 1. If F is bigger than that, my AC gain is less than 1. If FC is lower than that, my gain is bigger than 1. If F is much, much smaller than FU, then my gain is close to G0. So FU is also called the unity gain bandwidth, or the gain bandwidth product. So what does this all look like when plotted? Might give you a better idea. So just like the low pass filters, there's a relatively horizontal line, and then it starts to drop down linearly on this log-log plot after this characteristic frequency. So it has some DC value in terms of gain, some DC value G0, and then beyond this frequency F1, it starts to drop down in this linear fashion that we saw. Generally, my unity gain frequency is in the neighborhood of a few megahertz, sorry. So again, the ones that we have are roughly 4 megahertz as their unity gain frequency. So again, if I have a frequency that's relatively low, in my AC source, the gain is roughly the same as the DC gain. Once I get close to this characteristic frequency, 1 over 2 pi tau, depending on the tau value for this op amp, that's when it starts to drop down, and then my gain eventually drops down to 1 when I get to this unity gain frequency around 4 megahertz. If I keep on going, it's going to keep on getting smaller and smaller. So that was all for open loop operation. We can also look at what happens for feedback operation, so negative feedback in this case. So here I have a regular non-inverting amplifier with this feedback. Previous analysis, I know my DC gain is 1 plus RF over R1 using this notation for these resistors here. RF over R1 is the DC closed loop gain in this case. Closed loop operation, my gain V out over V in, both functions of frequency is AV, which is AV0. Again, the gain, DC gain, scaled by this factor, 1 plus AV0 over G whole thing squared. Also related to the frequencies. So 1 plus AV0 frequency over the unity gain frequency squared. And so my gain is the DC gain times F1 over F, or just FE over F over most of the frequency spectrum. So based on this equation, we can look at what happens for the frequencies. So again, if I have a frequency that's much less than the unity gain frequency, then my gain is the same as the DC gain, as expected. If I have AV0, F over FU equal 1, then F, my frequency, is FU over AV0, which is a new frequency called F3. And my gain is the DC gain divided by the square root of 2. Now this is a very special case. That's why it has a special name for the frequency. The gain being divided by the square root of 2. So remember that's voltage. My voltage divided by the square root of 2. Think about power. Voltage gets squared, so power in this case is exactly half. When power is exactly half, that is what is called the -3 decibel point. So this frequency F3 is the -3 decibel frequency. So that's why that's a special name. It's also why it's subscript 3 or 3 decibels. In last case, if AV0, F over FU is much bigger than 1, then my gain is FU over F. Again, at F equals FU, we have the unity gain of 1. So those are special cases for that equation. So again, kind of summary, general equation for the gain AV based on the DC gain, and can be scaled by either frequency. So we have frequency FU with AV0, or we can drop that out and get you F over F3, where F3 is unity gain over AV0. That's your -3 decibel frequency. So again, in terms of what that actually looks like, I have some DC value, AV0, and then at F3, that's where this straight line kicks in. And then my gain starts to drop as FU over F, then get down to unity gain bandwidth, and anything beyond that is going to attenuate, get less than 1. And so this portion below F3 is basically the usable frequency, because anything beyond that, the signals start to attenuate too much. So again, this -3 decibel place is where we kind of cut off the filters. So that's when we kind of say, okay, anything on one side of that stays, anything on the other side goes away. So same thing happens here. Anything above F3 basically gets attenuated, it gets filtered out. So same thing for these guys. Usable frequencies or anything below that. And so as the gain AV0 increases, bandwidth is going to decrease. So because I have this constant gain bandwidth product, straight line, if I keep increasing AV, my actual usable range drops. So if we look at the higher I go, essentially the more gain I have AV0, the smaller the usable ranges. So AV01 has a relatively high gain, but frequency range is smaller than say AV03, which has a smaller DC gain, but a much bigger usable frequency range. Again, the ones we have in labs, roughly 4 megahertz. So if my DC gain is roughly 100, F3 is about 40 kilohertz. So that's, again, about as far as we can go. Anything above 40 kilohertz, the gain's going to start to drop. If AV0 is only 10, so 10 times smaller, I then have F3 to 400 kilohertz, so basically 10 times bigger frequency range, but again, I'm only getting 10 times less the gain. But again, that's how that relationship works. So bigger gains are good, you get more out of it, but there's less frequency range you can use with it. Bigger frequency ranges make it better to use it for more frequencies, but you get less gain out of it. So that is the material for this week. As usual, I'll see you in class on Tuesdays for examples of this.